Okay, we're going to finish up. I think we're on 17, maybe. Yes, seems like a good chapter. So in this chapter, obviously, we've been talking about electrochemistry, and I believe last time we got into the idea of sort of non-standard conditions, and again, that's our Nernst equation there, which is what we saw this morning as well. Something like this, I think, something close to that. And that is E is equal to E naught minus RT NF natural log of Q. Again, we use this when we are not under sort of standard conditions. So much like a couple of your cells that you did today, you didn't have concentrations that were all 1 molar, so you would need to obviously use the Nernst equation there to do that. We also saw one that's really related to sort of the Nernst equation, which means when we are at equilibrium, E would equal 0 and Q would equal K, which gives this guy this here. And this is obviously the one where we could use to equal or figure out something that has to do with the equilibrium constant there in that case. And obviously our one that we did earlier, E of the cell is obviously E of the cathode minus E of the anode. Again, as we also talked about this morning, we use this one where we're not going to change the sign that we find in the SRP table. Again, that is the purpose of the subtract there. And if you do want to change the sign, nothing wrong with that. You could just need to make sure you add it, not subtract those two. We also saw delta G not relating it to it, NF of E. And again, the relationship here really between these two guys, positive voltage here results in a negative delta G, which means spontaneous should expect some products. And obviously opposite there, negative voltage would result in a positive delta G there. And that would be more non-spontaneous and reactants present at that point. We got into batteries and just a general idea of batteries, how they're similar and maybe different from a traditional galvanic cell. Obviously, they're self-contained. They still do the redox reaction. We also talked about corrosion. Corrosion is really, for the most part, the oxidation of metals. So anybody that has a SRP value there in terms of metals that is less positive than oxygen will pretty much go through corrosion. Again, with oxygen being more positive in that situation, the oxygen would act as the cathode in that reaction, while the metal would act as the anode and go through oxidation. Again, not all oxidation is necessarily bad. I can't create a layer that will protect underneath. So I think that's sort of where we left it off there. Any questions on any of that stuff there? All right. So the last thing we're going to talk about in this chapter is electrolysis. And electrolysis is the process by where we basically apply electrical energy to cause a non-spontaneous reaction basically to occur. So for example, if you took just sodium chloride and you wanted to, break it back apart into its elements, sodium and chlorine here. A little two there. You would have a very hard time to do that, just heating it up or anything like that. If you ever did, it would not obviously break back apart into its sort of original form there. So we can apply an electrical current like a battery, and by doing so, we can generate back sort of the elemental components that occur here by doing that. So our sodium chloride goes in, out comes the chlorine gas and really sort of the liquid sodium that comes out in this process. You could also do this with water, like a nice 9-volt battery and a couple electrodes and some water, and you can basically break water back down into hydrogen gas and oxygen gas. Now, because this is sort of the reverse reaction, if you will, of kind of putting it together, and our anode and cathode reactions are a little bit different than what you might expect them to be or might just automatically go to. So when we sort of do the opposite of this reaction, or the one we normally think about, which is actually the formation there of sodium chloride, So we take some sodium plus some chlorine and makes our sodium chloride in this case. What's happening in this case is it is the sodium that is obviously losing the electrons, right, and becoming oxidized, and would be our anode sort of reaction. The chlorine here is going to be our cathode reaction. And this is sort of a normal redox reaction here. But now when we're talking about really doing the process opposite of that, and the electrolysis sort of process, we are taking sodium chloride and again breaking it apart into sodium and some chlorine. In this particular case, we are going in terms of just the sodium here, we're taking 2 sodiums and we are actually gaining a couple of electrons to make our sodium with no charge. So it is actually going from +1 to 0 here, the sodium. And in that case, it is actually the reduction that is happening here. And it is actually going to be our cathode in our electrolysis cell. Same thing if we look on the chloride there, we're actually starting with the chloride with a charge, and it's going to actually end up with chlorine with no charge on this side. So it's going from -1 to 0 in this case. It is becoming more positive, and it is actually going through oxidation, and it will end up being your anode in an electrolysis cell. So it's a little bit opposite of obviously making sodium chloride, is breaking it back apart. So our anode and cathode basically switch in an electrolysis cell here. And that's what we see here. We see our chloride as our anode, and we see our sodium as our cathode in this case, because the goal here is really to create the sodium and the chlorine gas in this particular case. Any questions on that there? Obviously, some type of battery could supply the extra electrical energy needed to basically overcome the non-spontaneousness of that reaction. Also occurs with electrolysis of water here. And again, a simple sort of reaction. You basically need to make your water a little bit acidic. So you got to add a little acid to it, build up some of that H+ ions that are in that solution. But you attach a battery and you can run it, and it will start to break apart water overall here into our hydrogen gas and our oxygen gas in this particular case. And I suppose do a little balancing here, like it's chemistry, do a little bit of that. So in this particular case, if we look at hydrogen, what is happening is hydrogen starting at +1 and actually ending at 0 in this case. So it is the hydrogen that's actually going through reduction. And in this case, we look at the oxygen, which is -2, ending up at 0. So it is going through oxidation, and that is what we see down here. We have our water basically going to oxygen, and here's our hydrogen being formed here from the H+ in this particular case. So once again, our anode cathode sort of opposite of putting it together. We're basically breaking it back apart. You'll need some type of acid involved here. Like I said, just sort of beef up sort of the H+ concentration in the solution of water and help this process along. And if you do this, this is what you'll see is the bubbles that will occur here in those test tubes. And those bubbles obviously are the hydrogen gas and oxygen gas being made. In the empty spot of the test tube, right, is where our gases are, our oxygen and our hydrogen gas basically end up there. Why is there more hydrogen gas and oxygen? It is H2O, yes, twice the hydrogen to oxygen there, yes. So you get twice the amount of hydrogen gas to oxygen gas when you do this sort of process. Now, water is a weird one in a sense. When you're doing some type of electrolysis problem, sometimes they really don't just come out straight and say, hey, you're doing the electrolysis of water. Sometimes they'll mention something like sulfuric acid in an electrolysis cell, and that's sort of all they'll say. So if you see something that has to do with electrolysis and it says something like sulfuric acid or some type of acid, it is probably the electrolysis of water that's taking place, and these would be your half reactions, obviously, that you would use for that type of situation. Any questions on that there? So let's talk a little bit about electrolysis problems and sort of how we go about it. So a lot of times in an electrolysis problem, they will tell you how long you're running the cell for, and basically at what amperage there that you are running the cell. And this relationship here, that a coulomb is equal to an amperage times a second, is good because an amperage is a coulomb per second. So that means the time usually needs to be also converted to seconds. So everything will cancel out. And typically, almost most of the time in these problems, you're going to take the time, which is converted to seconds. You're going to times it by the amperage, which is really a coulomb per second. That will allow the seconds to cancel out. And you'll end up with basically a coulomb of charge for whatever your cell is. That is then when we typically will then use Faraday's constant down there, which is our 96,500, to go from coulombs of charge to moles of electrons. Coulombs cancel, gives us moles of electrons. It's at this point where the half reactions come into play. So you should have your half reactions. And you could do sort of like a mole to mole relationship between the electrons and the half reaction and whatever you're interested in. So, you know, if we did have something like what I wrote there before, I think, which was Cl minus plus, whoops, goes to Cl2 plus a couple of electrons. So if we were interested in chlorine, for example, we could say for every 2 moles of electrons, I get 1 mole of Cl2. So that is typically what you do next in terms of going from electrons to whatever you're interested in. And it's at this point, it sort of depends on the problem. You may be asked how many grams you would produce in the cell. So once I have moles, I could go use the molar mass, right, to go from grams to moles. Or the opposite way around, moles to grams would be good, the molar mass. Now, also sometimes a lot of these electrolysis cells will collect a gas. So sometimes we're not interested necessarily in how many grams, but we're interested in volume of gas that we collect. And since it is a gas, we will sometimes need to use PV equals nRT here to help us get there and solve for volume. A reminder, pressure needs to be in atmospheres, right? And should be moles. R is R 0.08206 liters, atmosphere, Kelvin, and mole. And T obviously is in Kelvin. So very commonly in these sort of problems, we do kind of use the ideal gas law at the end there, especially if we are dealing with something that is a gas, or if we're looking for grams, molar mass at the end. So those are the typical sort of pathway to these problems. Take how long you run the cell for, times the amperage, gets you coulombs, use Faraday's constant to get to moles of electrons, use the half reactions to go from moles of electrons to what you're interested in, and then basically do a conversion at the end there. Any questions on that there? All right, then we'll come back to this one here. Why don't we do this one first here? All right, so let's say we are running a cell here, and we want to know how many grams of calcium here will be produced in a cell that has molten calcium chloride if the current is 0.452 amperage is passed through the cell for 1.5 hours. So why don't you take a second or two and see where you get to here. I think calcium is 4008 maybe ish, give or take. Let's see how you're progressing. So it's an electrolysis cell. So obviously we're going to take our calcium chloride, basically break it back into sort of its elements, which in this case would be calcium and chlorine gas. Now, in this particular case here, we will look and see what is going on. On the left-hand side, that is +2 for our calcium to 0. So our calcium is actually, again, going through reduction, right? Which means basically the calcium is starting with a +2, and it is gaining a couple of electrons to form our calcium there. Now, if we look at the chloride, on this side is -1 and 0 on that side. So again, it is going from -1 to 0, which means it is becoming more positive, which would be our cathode in this case. And in this case, it's going really from 2 chlorides down to chlorine plus a couple of electrons in this case. This is our oxidation that's occurring. That obviously would be our anode part. Any questions on that there? Okay, so again, we kind of start these things very similar. They did give us the amperage, which is 0.452, and we can convert that into coulombs per second, which is an amp. We are running it for 1.5 hours. So once again, we do need to convert those the time into seconds. So 1.5 hours. In an hour, there's about 3,600 seconds. That gives us about 5,400 seconds here. Once we have it in seconds, we again can use our amperage. And it's really the same number, just change the units so you can see it cancel. Coulombs per second. Those guys cancel. That gets us about 2440.8 coulombs. Any questions so far? Now we're going to use Faraday's constant really to convert us into moles of electrons. So that would be our next step here, 2440.8 coulombs. There's 96,500 coulombs per mole of electron. Once again, here the coulombs will cancel. Dividing that out gets us, we'll call it 0.0253 moles of electrons. Really, at this point, we could tackle both. We could do chlorine and calcium at this point, but we will just do the calcium, which is what it asks for. So in this particular case, if we look at the balanced half reaction, we see that for every 1 mole of calcium there, we have 2 moles of electrons. So we're going to use that as our conversion factor here. For every 1 mole of calcium, 2 moles of electrons. So taking our 0.0253 moles of electron and using that conversion from the half reaction, basically divide that by 2, 0.0126 moles of calcium would be produced, which we can now use the molar mass from the periodic table up here to convert that into grams. So if we take 0.0126 moles of calcium, times it by the molar mass of 4008 grams per mole. Moles will cancel, times about 4008. Gives us about 0.51 grams here of calcium would be produced in the cell. So if we ran the cell for 1.5 hours, we should get about 0.51 grams of calcium to come out. Any steps, any question on any of those steps there? Like I said before, if we were also interested in chlorine, at this point, we could use our moles of electrons and again, use the chlorine half reaction to figure out how many moles of chlorine that would be. And once again, we could either get the grams, or if you had some pressure, some temperature information given to you, you could use the ideal gas law and figure out maybe something like volume as well. Any questions on any part of that calculation there? All right, so I'll go back and do that one we skipped here. So we're going to do a electrolysis cell that runs at 1.26 amps for 7.44 hours. Write the half reaction and calculate the volume of gases generated. We're doing a cell containing sulfuric acid and nothing else mentioned. So this, once again, is the electrolysis of water is what's going on here. So I'll give you the half reactions there, and that would be these guys here. And we're running the cell for 1.26 amps. And we're running it for 7.44 hours. What is the volume of both gases, oxygen and hydrogen, at STP? STP is standard temperature and pressure. That means temperature is 273 Kelvin, right? Pressure is 1 atmosphere. All right. Take a look, see how we're doing. So once again, you can kind of start it the same way. This is 1.26 coulombs per second. That means we probably want to also convert our hours into seconds. So 7.44 hours, 1 hour, 3,600 seconds, 7.44 times 3,600 gets us 26,784, looks like. At this point now, we really got it in the right units, so everything cancels here correctly. So we'll multiply that by the amperage at which we ran the cell for. Seconds. And our seconds here will cancel times 1.26. Gets us something like 7.84 coulombs. Once again, here we're going to use our Faraday's constant and 337. I'm just gonna kind of round that a little bit. 48 coulombs. We're going to use our 96,500 coulombs per mole of electron, giving us something like 0.3497 moles of electrons. Any questions so far? Now that we have that, we can figure out the moles of each gas since we're interested in it. And we could go to the half reactions here and find our electrons to our gases. So we can see from the first one there that for every 4 moles of electrons, we get 1 mole of O2. 1 mole of O2. So we'll do that to figure out the moles of O2 here. That is basically going to divide this guy by 4. It's going to get us something like 0.0874 moles of oxygen. We could also do the same thing coming to our second half reaction, which there is a 4 here that would get multiplied here, and that would give us 4. And we would also multiply the 4 into here. That would give us a 2. So we would basically have 4 moles of electrons to 2 moles of hydrogen. That is the same as 2 moles of electrons for 1 mole of hydrogen. So you can use either one, obviously, in this case. So we would start again with our moles of electrons. And again, they both should give you the same, but I'll just use the whole thing there. So 4 moles of electrons, 2 moles of H2 gives us 0.03497 times 2 divided by 4. 0.0175 moles of hydrogen in this case. Any questions on that there? At this point, we got a number of information. We obviously have our temperature, which is 273 Kelvin. We have our pressure, which is 1 atmosphere. We always have R, which is 0.08206. And now we have N, obviously, here. That means we could use PV equals nRT, if you like. And obviously, we would be solving for volume in this case, as that's the only thing we don't have and what we're looking for. So let me do that there for oxygen. Flip the page here so I got somewhere to write. The volume of oxygen, PV equals nRT. Solving for V would be nRT divided by P. And put it in our moles for oxygen, 0.0874. Putting in our R. Our temperature and our pressure here. Everything's going to cancel out except for the liters, and that would get us 0.0874 times 0.08206 times the 273 gives us about a 1.96 liters of oxygen would be collected at this point. We could also do the exact same thing here using the moles of hydrogen here. And once again, our volume would be nRT over P. The only difference here, obviously, is we want to make sure we use the moles of hydrogen, which would be 0.0175. Everybody else here will be exactly the same. And if we do that there, 0.0175 or 0.08206 and a 273 I feel like I added an extra 0, did I? I did, right? I did, I think, maybe 0.3. So I did add an extra 0 here. Sorry about that. That is 0.175. That would make then this 0.175. And a much better answer, I think. All right, let's try that again. 0.08206 times the 273 gets us a 3.91 or 2 liters of H2 in this case. So sorry about that. So it should have been obviously here just 0.175. I think I wrote an extra 0. First off, any question on either of those calculations? Could I have solved these guys a different way? And I could have, because we were at STP, perhaps you remember 1 mole of any gas is 22.414 liters. So you could have just took the moles, for example, of hydrogen and use the right number there. That would be good. And times it by 22.414 liters. All should cancel, should get you there as well. So you could have done that because it was at STP conditions. Remember, you could only use that if it is STP conditions. So that's another way you could have solved it here. Any questions on any of those calculations? We do see here pretty much what we saw in the picture. We got about 4 liters of H2 and 2 liters of O2. So twice as much H2 in this case than O2. Question on electrolysis problems. Variation on this problem is they tell you how much you collected basically, and you work backwards and maybe you figure out the amperage of the cell or how long you ran the cell. So kind of working backwards is like a variation, obviously, on this problem. That should wrap chapter 17. And that should be the very last thing that will be on our exam, which is 1 week from today. Yes. We're out to chapter 19 here, which obviously, like I said, is not on the exam. Will be on the final. We're talking a little bit about transition metals. Just to remind you maybe about some things that maybe you learned before about transition metals. We then will talk about complex ions in this chapter and coordination compounds and how to name all those things. So a little bit about obviously some transition metals here to sort of open up and some properties of them. One thing that you might have learned was referred to as effective nuclear charge. And that's sometimes referred to as Z effective. And that is the positive charge that's found on electrons as a result of what is sometimes referred to as shielding. So for example, if we had something like our good friend lithium there, lithium is 1s2, 2s1, right? So lithium has got like a +3 nucleus with his 3 protons that are there. And in sort of that first energy level, it's got the couple of electrons that are floating around. And sort of the second energy level, it's got 1 electron floating around. Now, when we think about sort of the idea of shielding and sort of the charge that everybody is feeling, or the effect of the charge that everybody's feeling, the strength of things that are oppositely charged, attraction to each other, does increase with sort of the size of the charge. So really, these guys up front here on the lower energy level, they are feeling basically the full brunt of that +3 charge, and those guys are going to be held really tightly. Now, when we get to sort of our highest electron here, right, which is also known as the valence electron, right? And these guys are referred to as core electrons. This guy is actually shielded a little bit from that full brunt of the +3 charge. Again, kind of like if you said in a movie theater in the center, you can see the screen. Somebody comes in, right before the show starts with the big cowboy hat, sits right in front of you, just shielded some of the screen from you. So the same thing happens here. What ends up happening is, because these electrons in front are sort of taking on some of that positive charge, the electron that's the valence electron only feels a smaller positive attraction to the nucleus, is not held as tightly. You could actually do a little calculation by Z effective. You could take the atomic charge there, positive guy, minus the number of shielding electrons, which in this case is 2. That means our outer electron here is actually only feeling a +1 attraction to the nucleus. And that is why which electrons are involved in bonding? It is the valence electrons, right? Those outermost ones, because they're not really held as tightly. And that means that they can be removed easily or shared a lot easily. So when we look at sort of the periodic table, the general trend in sort of effective nuclear charge is that it does get a little bit larger as you go from left to right on the periodic table. What we're looking here is period 3 there on the periodic table. And you can see the effective nuclear charge increases as well. As you go to the right on the periodic table, you also have more protons, which means bigger positive charge, bringing everybody closer, right, and holding tighter. And that is also why we also see the radius or the size start to decrease as you go to the right on the periodic table. Again, greater positive charge brings everybody closer in, even those outer electrons, which are further away. And again, that's why we see this sort of trend here when we look at it. Now, specifically, the transition metals are between group number 2 and group number 3 there on the periodic table. Are transition metals. You remember transition metals as, probably from naming, obviously, the ones that need Roman numerals, except for silver, cadmium, and zinc. And that is because they can make multiple types of charges, right? Copper could be +1 or +2, depending on the situation. Iron +2, +3. So you do need to give sort of the Roman numeral to indicate what the actual charge is. Transition metals start in the D block, right? And these are sometimes referred to as the 2 bottom rows as inner transition metals, because technically speaking, they go right about there on the periodic table. Those guys, right? Technically go there if you follow the atomic number. They're sometimes referred to as inner transition metals, which are the F block, right? And obviously, For reminder's sake, that is the S block there, right? And that is the P block there in terms of electron configuration when you look at it. Also a reminder that although this is period 1, period 2, period 3, period 4, D's start at what energy level? 3, so that is 3D there, right? Not 4D, so it is 3D. Underneath it would be 4D, underneath it would be 5D and 6D as you go there. And by the way, F start on the 4th energy level, right? 4F happening over there. So transition metals do show very great similarities within a given period. Are a group on the periodic table. So guys that are sort of grouped together do have very similar sort of characteristics. When they do form ions, they can form more than one oxidation state. A lot of times complex ions, which is a metal in the middle, and a bunch of ligands that are attached to it. Form these what are referred to as complex ions. And a lot of times the metal in the middle is a transition metal. And our ligands here, as we will talk about, are what are referred to as Lewis bases, right? Lewis bases are things that do what? Lewis electrons. They do, they donate the electrons. Yeah, so Lewis bases will donate a pair of electrons, right? While Lewis acid is one actually that will accept a pair of electrons. In this case, sort of the metal is acting as a Lewis acid because the metal will have a positive charge, right? Which means that it is electron deficient and willing to accept those electrons in a complex ion situation. Remember, we talked a little bit about it. We'll talk more obviously in this chapter as well. But things that typically have like a negative charge, like chloride is a good Lewis base. Things that are polar that have non-bonding electrons, like water is a very good Lewis base. And ammonia, you know, these are things that are good Lewis bases. They have pairs of electrons. They're polar, or they are negatively charged, which by definition means they have more electrons to become negatively charged. So they're willing to do that. And here's a picture, obviously, of a complex ion. This is cobalt with 3 ammonias attached here. And again, they're attaching through the nitrogen there, which again is acting as our Lewis base and donating those pairs of electrons to our deficient cobalt in the middle of this case. And we get this complex ion. Overall charge of the cobalt here is +3 because NH3 is neutral, right? There's no charge to any of those NH3s. So that's where the +3 charge basically comes from. You will, by the time we are done with this chapter, know how to properly name this guy right about there. You'll call it hexamine cobalt 3 ion and be happy about that at some point. So you'll actually know how to name these guys when we're done with the chapter. Well, let's continue a little bit our talk about transition metals, ionic compounds with transition metals. Most compounds have a specific color depending on sort of the charge of the transition metal and also really the ligand that's attached. You could have really the transition metal that has the same charge in 2 different complex ions, and sort of depending on the ligand, you will get some different sort of colored solutions. Maybe in one case it may be blue, in another case the solution may be pink. Many compounds are paramagnetic. Paramagnetic means they have at least some unpaired electrons. Yeah, so paramagnetic is some unpaired electrons happening there. Electron configuration. So electron configurations for transition metals, as we talked about a second ago, really the first row transition metals there, which is number 21 there and on, is our 3D area there. This is what's sometimes referred to as noble gas configuration, right? The thing in the bracket represents the configuration for argon, right? 1s2, 2s2, 2p6, 3s2, 3p6 in this case as well. There are several exceptions to electron configuration. By the way, I hope you know how to write electron configuration still, right? Yes. S is 2 maximum electrons, right, in an s orbital. In a p subshell, it is 6, right? D subshell, which there are 5 different ones, right? Each could hold 2, is 10. There are 7 different F sub orbitals, which each could hold 2, which obviously gives you 14 max. By the way, just in case you're not sure, S's start at the first energy level, P start at the second, D start at the third, and F start at the fourth. And then frankly, all you need to do is just fill in the numbers underneath, yes, and use the right letters there. There you go, 3S, 4S, 5S. I'll learn to count one of these days. 6S, 7S, 3P, 4P, 5P, 6P, 7P, 3D, 4D, 5D, 6D, and 5F. And perhaps you saw something like this. Yes, you zigzag around. You start here always and just keep zigzagging back and forth, right, until you get the right electron configuration. There are several exceptions. Chromium and copper are 2 common exceptions that most people learn about, and the exception is if you follow that zigzag thing, chromium is 24, which means you would write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. If you just follow that, the exception obviously occurs here where there is an extra electron from the S up there in the D, and it should end up being 4s13d5. That puts a parallel electron into each of the d orbitals, right? Maximum stability is found by parallel spin of your electrons, right? Which is why electrons go into the orbitals one at a time, right? And then come back and pair off when there are multiple orbitals within a subshell. Same thing happens with copper, and it's able to happen that way because, as you probably also remember, when you have the 4s orbital, it is very close to the 3d orbital in terms of energy. And when electrons go in, it actually goes in like so, right? What happens once we start putting electrons here in terms of energy? Anything? It actually switches energy levels, and the 4s, for example, actually becomes higher in energy than our 3d after you start populating the d orbitals. And that is why when transition metals lose electrons, they lose which ones first? They lose the s's first because of that switch that occurs in terms of energy. But in terms of filling order, they do go into the s's first and then the d's, but then there is a switch. That is why sometimes you'll see people write electron configuration like 3s2, 3p6, 3d4, 4s2. And that is based on energy rather than filling order. Probably 99 times out of 100, you should be writing it in filling order, which has the 4s comes first and then the 3d. Also, you might also remember that on the periodic table, pretty much if you go below chromium and copper on the periodic table, there's very similar exceptions to the electron configuration. For example, PD there has no electrons in the S. They've all been promoted up to the D. Silver also is an exception as well. So right below chromium and copper, kind of down in the middle there, there's a lot more exceptions to sort of electron configuration. And maybe you remember some of those or saw some of those. So as I mentioned before, because of that sort of transition that occurs or change that occurs with the energy of the orbitals, pretty much all transition metals, once they start losing electrons, they pretty much will always deal off the s electrons first, and then if necessary, they will then go into the d orbitals if they have more than 2 electrons that need to be lost. So that is basically what happens here. So that's what we see here when we look at Ti, and then Ti with a +3 charge. Obviously, a +3 charge means that it lost 3 electrons. So once again, if we sort of filled in our electrons here, what would happen is it would lose these 2 electrons first and then pluck off 1 more here from the D. That leaves obviously our 1 electron left in the d orbital when it does have that charge. Any questions on that there? All right, why don't you not explain this? Why don't you write the electron configuration for iron 2 and why not iron 3? And while we're at it, let's do a nickel 4. So iron is number 26 there on the periodic table, and nickel is 28. So if we just looked at iron with no charge, it would be 26. So if you went longhand there, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and there 2, 4, 6, 3d6 there. You went shorthand, you would do a little argon action, 4s2, 3d6, as the argon obviously would cover everything through there. So in this case, with our +2, it will then lose these 2 electrons first, which means this guy would be argon 3d6 in this case. Any questions on that one? Now with the +3 means it lost 3 electrons, which once again, it would lose those 2 and then has to take 1 out of there. And that would give us a argon 3d5 in this particular case. Any questions on any of those 2 there? Nickel, again, with no charge would be a little argon 4s2, 3d8. So a +4 would mean it lost 4 electrons. So we would definitely take the 2 out of here. We then would have to grab 2 out of the D at that point, and that would give us something like a argon 3d6 in this case. Yeah. Question on either of those? These 2 have the same electron configuration. Yes. That is known as being isoelectronic, right? With each other. The 2 things that have the same electron configuration is isoelectronic, like neon and oxygen with a -2 charge or oxide. Any questions on flashback Tuesday electron configuration ready? Yes. No? Okay. All right. We'll talk a little bit about oxidation states of these first row transition metals. And as we saw in the experiment the other day, our good friend Mn right here has a lot of oxidation states, as we see there. We kind of see a rise, and again, this is the first row transition metals, 21 through 30-ish. And we do see it start to increase as we hit Mn, which is sort of right there in the middle of that row. And then it kind of comes back down. Again, most popular, I guess is the way to word that, I suppose. Oxidation states +2s, +3s, and some +4s. But you can see something like Mn can get up to +7, and all these other sort of oxidation states that can occur. So we sort of see a peak of oxidation states and sort of drops back down as we come to the other side. Another sort of trend in terms of transition metals is ionization energy. Ionization energy is the energy that's required to remove an electron, right, from the gas phase of an atom. Trend in electronegativity, trend in ionization energy overall on the periodic table is, as we go up and to the right, what happens? Increase or decrease ionization energy? Yeah, it increases, right? And it decreases as you go down overall in terms of ionization energy. When we talk about ionization energy, this is the energy to remove an electron. When somebody removes an electron, you become what type of charge? Positive. So oftentimes we think about ionization energy in terms of cation formation, right? Or positively charged guys. Electrons come off all at once or one at a time? They do come off actually one at a time. So electrons pop off basically one at a time. So for example, if we took our friend magnesium there and it would then lose one electron, and there would be an ionization energy for that, which is like the first ionization energy. What would then happen is that magnesium there would then not start with a +2, but start with a plus there, I think in this case. Back here. Let's try this again. The guy with the +1 would then drop another electron. And that also would have an ionization energy associated with it, which is known as the second ionization energy. And lastly, that second guy there would drop off one more electron, which would be known as the third ionization energy. And make a +3 charge. So easier to remove the first electron or the second or the third electron? The easiest one to remove would be the first electron. Yeah, so the very first electron is the easiest. When you remove the electron, the overall size gets larger or smaller? Smaller, right? You lost an electron cloud gets smaller. That means those outer electrons have now just moved closer to that positive charge, right? Which means it's going to be held a lot tighter and can take more energy to remove it, the second electron, which then you then recess down a little bit further, right? And again, that third electron gets even harder to remove. And that's what we see on this table is this is like the first ionization energy, second, third, and they each basically represent one electron being popped off. You can see something like magnesium, which I wrote up there. It takes about 735 kilojoules of energy to remove the first one. Not too bad. Then it doubles in energy to remove the second electron. And then if you want to then try to remove the third electron, it like goes up by like 7-fold, which pretty much doesn't happen. And that is why magnesium, which is group number 2, typically ends up with a +2 charge. That's also why if you look at magnesium's electron configuration, 1s2, 2s2, 2p6, and 3s2, after it loses those 2 electrons, which is the valence electrons, what is left is the core electrons, right? Which are really now very much closer to the nucleus and pretty much do not get removed. So at some point there becomes almost like an energy barrier to remove those core electrons, and they really don't happen. And we see the same effect here with sodium, right? Which is typically a +1 charge. So popping off the first one, not too bad, but it's about 10-fold the energy there if you wanted to try to rip in there and take off the core electron. So the general trend that we see between, again, first, second, third, and so forth, ionization energy is it starts to increase, obviously, every time you sort of take off an electron. It's harder and harder to remove an electron. And that's why there's certain things, as you learned on the periodic table, that have pretty much fixed charges because, you know, you get into those core electrons and it gets much, much harder to do. Any questions on that there? Here's some properties of these transition metals. It's clear you should memorize everything on this chart. No, I'm just kidding. But you know some of it, hopefully. But atomic number obviously increases as you go to the right. Electron configuration we talked about. Overall size and radius decreases upwards and to the right on the periodic table. This is just another ionization energy in different units, but we do see obviously the increase as you go to the right on the periodic table, and also an increase as you go from first to second to third ionization energy. Our common oxidation states, as we talked about there, +2, +3s. We also do see a slight increase in density as you go to the right. And that again is more electrons, bigger volume, and bigger mass as well. And here's our ionization comparison of first to third. And we see first much lower than the third. Here's all three of them in case you missed the second ionization energy and wanted to see it on the graph as well. Electron affinity is another trend that maybe you talked about. Electron affinity is basically the negative energy change that occurs when somebody gains an electron. So this is basically the energy change when you gain an electron. When we gain an electron, you become negatively charged. So we usually associate electron affinity with anion formation, which is our negative guys that are being formed there. Electron affinity is different than electronegativity. Electronegativity is the ability of an atom to bring electrons to itself. Electron affinity is the actual energy change that occurs when it accepts that electron that occurs. In general, electron affinity does follow kind of like you'd imagine, I assume. It increases up and to the right, kind of decreases as you go down. It's not perfect, as you can see here, kind of increases as we go up, but then kind of comes back down a little bit. So it's not a perfect sort of trend, but that's the overall general trend, is increases as you go to the right and decreases as you come down. All right. This is a table relative reducing abilities for each of these guys, and reducing ability increases as you go up there, which means the guy up on top would be our guy that would be oxidized, right? And would be a good anode. Now you may be saying to yourself, shouldn't the guy that's more positive be our cathode? And that would be correct, except that these reactions are written as reduction or oxidation reactions. In this table, these are all oxidation reactions, yes? So if you want the reduction like you would find on the SRP table, you pretty much would change the sign for everybody here. And that would be all negatives coming this way, which means this guy would be positive, and this would be our better cathode in that case if you were doing SRP. So this is what is sometimes referred to as the standard oxidation potential here, as you are all written as oxidation ones. And just to finish out for today, here's what they look like, the first row transition metals there, in case you're curious. And these are different charges that they can make and oxidation numbers that they can make, which you don't have to worry too much about. All right, that's a good place to stop, I think. Any questions?